So, hello everyone. Welcome to the second day of our colloquium. We have 6 exceptional speakers today. And I'm glad to present our first speaker, Mohammad Hosseini. And yay! Okay, your 15 minutes is go.
Just 15 minutes, right?
Wait, why you get chocolate?
Just in case.
No, give chocolate back. It's for people who ask questions. So, yeah, you are welcome to listen, and then you can ask questions, and you're gonna get a prize.
So, hi everybody, my name is Mohammad Hosseini. I did research with my supervisors, Joseph Peters and Shervin Sheikh Mohammadi from Simon Fraser University and University of Adam. And my thesis title is Energy Budget Compliant Adaptive 3D Texture Streaming in Mobile Games. Here are some motivations. Well, you know that energy consumption is important for mobile games. And also we know that energy demands are increasing in a faster way than battery technology. Nowadays battery technology are actually behind the other technologies. You have your smartphones, you know that for instance on mobile devices, I mean like smartphones, actually the battery is not lasting more than 24 hours. 3D games and online environments are becoming more and more popular nowadays. And 3D textures are bulky, so being bulky means that they need high energy demands to be transmitted via wireless networks. And also wireless circuits consume a significant amount of power. I mean wireless circuits means wireless network interface card with controller, which we call it WNIC, which is one of the most important parts in the mobile devices to consume power. So what are our goals here? We want to increase the battery life by decreasing the amount of energy that is being used by the wireless network interface controller. And also another aim is to maximize quality of the 3D textures. So actually we have an energy budget, we estimate a download budget out of it, and then we want to actually maximize the quality of transmitted 3D textures out of this budget. Let's say that you know textures are actually kind of photos that are actually covering the outer space of 3D objects. In games, you must know that what are textures. They are being stored on mobile devices when you are playing games. So they're actually the physical view of the 3D objects, or 3D meshes, let's say. So here in our work, we assign importance values to textures, and the quality, our defined quality is actually a multiplication of importance and size. People are all eating, nobody is here to me.
Wait, no.
Okay, that's okay. So we want to selectively reduce the sizes of textures to reduce the actually size of the textures, so to reduce the cost of wireless controller to transmit the textures out of the, via the wireless network. And yes, of course, we want to send the most important textures first, and then the less important ones. So what will be our results is that, we want to have an adaptive streaming, which is good for increasing the quality. And we know that it's a kind of priority-based streaming, which actually brings more quality than other approaches like non-priority-based streaming. They don't give any difference for the textures, whether they are important or not. They just simply transmit all of them without any classification for the textures. So this is actually the overall overview of our system. At the client side, we have the energy budget. Client side means a mobile device, a smartphone, let's say. So it has a kind of available budget. It's energy. And we send it to the server side, which is actually kind of networking to receive. This budget is then actually being let's say formulated to a download budget. I mean the energy budget to the download budget. And then we have an adaptation here. We have a classified texture list, and then we apply our heuristic algorithm, then apply our texture compression, which is a kind of simple downsampling for the textures, and then we will have our output textures. So to transmit them using 3D streaming approach to the client side again, and the client side will actually receive the textures and then some internal things, buffer manager, and then deserializer, and then 3D renderer using OpenGL, so you can see the textures and the graphics layer user interface. So this is the progressive streaming. You can see that, for instance, progressive streaming here in our thesis is actually means progressively stream the textures. So actually, I don't know if you can see here, some objects being the first picture, then the other objects, and then completing the scenery. So in our work, we want to make them kind of using priority. So the most important ones first, and then the other objects. So yes, we said that user sends the energy budget to the server, and then server uses a kind of linear model. We know that from the previous works, how to estimate energy for wireless network interface controller are kind of like linear model. So we have a kind of establishing connection, energy for establishing connection, plus the amount of size of the data to be transmitted. And then we estimate the download budget out of this, the energy budget, or let's say download budget, both vice versa, to estimate the other one. This is another proof to say that energy and download budgets are kind of in a linear way, working in a linear way. So here comes our heuristic. We have a list of textures, T1, T2, T3, and so on. We have a budget W, which at this point we assume that this is too small for all the textures, so we cannot transmit all of them. So we have a smaller budget to transmit the textures. So what we are going to do is to select and stream a subset of them, not all of them. I mean, we are transmitting all of them, but actually instead of transmitting a subset of them, which is actually a kind of 0-1 knapsack problem, we want to transmit all of them, but some of them with reduced quality. This is a different approach. So as we said, each texture has a value VI and a size WI. So this is simply a knapsack problem that we want to maximize the value of the object, the textures, subject to not actually exceeding the available budget. This is empty part, but we have good approximation algorithm for that. And we know that if you use 0-1 knapsack problem, you will have poor gaming experience because we have to transmit, we don't have to transmit some of them, so some of them will be missing. These are, you can compare the, I don't know if you can see here. So if you don't transmit some of them will be like that, which is not very good in our gaming experiences from a user perspective, and also other perspectives. And about our texture compression, we said that we are sending all of the textures, and we want to compress some of them so to fit within the download budget. Compression here means actually reducing the quality, because we define quality actually as a kind of a multiplication of size by its relative value. Value is how important the textures are. So as we said, the first one is actually not using our approach, I mean, without any prioritization approach. And the second one is how our texture compression works. So the first one is another picture. The first one is our approach. You cannot see how the difference is. And the second one is full streaming, not having any budget. Our texture compression is, as we said, is a kind of simple downsampling. You know that mostly in games, the texture resolutions are mostly a power of 2. 512 by 512, 256, 256, and etc. And we apply downsampling because we wanted to make it as simple as possible. So downsampling is the simplest way we can use for reducing the size and the resolution of the textures. What we do here is, it's kind of simple. We get a kind of simple block as a representative texel and a representative texel out of it, and then we want to divide these whole textures by these many blocks, and then out of these representative texels we want to match them and then reduce the size. In terms of programming, it's kind of very easy. So actually, for instance, yes, if you want to reduce the size will be actually divided by factors of 4. 4 to the power of I. I don't have time to actually explain more. It should be easy. So yes, for instance, 512 by 512 will be 64 by 64 if the I here is 3. So we will have actually 64 blocks here. In a kind of intuitively explaining, the picture will be look like that. For instance, if you downsample 512 by 512 to the 64 to 64, you can see the difference here. And if you apply the texture to a 3D model, these are going to be the differences. And here, for instance, the first one is 512, the second one is 256, 128, and the third and the last one is actually not transmitting anything, so an empty, let's say, 3D mesh or 3D object. We use simple downsampling here, but we know that there are also some other sophisticated compression methods also, like bilinear, by cubic, and trilinear. They bring better quality, but also they will increase the processing overhead. Of course, our method is kind of very general with any other compression approaches. We are not caring about that. These are the differences between, bicubic and our simple downsampling. These are the relative execution time based on our machine, that how much bicubic, bilinear, and TCM, which is actually our texture compression method, is doing in our thesis. So the main problem statement is here. FPD, do I have time?
2 minutes.
2 minutes. So we have a list of textures. The first one, C1, is actually representing the important class, and the C2 is actually representing the not important, or let's say less important, because if you are saying not important, there is no need to transmit them. So all the textures are important, but within different priority. Yes, we want to stream the textures within the available budget, which is W, and the textures in C2 and C1 have a relative value V1, V2, according to each other. And we have an Rmax, which is actually the maximum acceptable reduction in size, or let's say reduction in quality, which the user actually defines it. So now we are going to actually send the textures with these classification within the download budget of W. So to maximize the quality of all the textures to be streamed. So here we have 4 different cases. If S, which is actually sum of S1 and S2, is less than W, then of course we can transmit all of them. There is no need for compression. And then 3 other cases here. The second one says, I will just explain them. So the first one is that our budget is more than the sizes of all the textures, so there is no need for compression. The second one is that W is less than S divided by R max. So if we just compress all of them with the maximum amount, then we cannot still fulfill our available budget. So problem cannot be solved. So 2 other cases here. For the third case, S1 can be transmitted quite as it is, and C2 needs to be compressed using our heuristic. And for the fourth case, actually, we still cannot also transmit C1, the important textures. We also need to compress them as well.
Conclusion.
And we have a kind of heuristic here, and our algorithm is kind of simple. Our experimental setup is using 3D self-runner demo with progressive streaming. We have almost 100 textures, different percentages. This is our server, our client, special device for measuring the power using Power Tutor Profiler. Different measurements and different criteria for measuring the qualities, the energy, and different things. These are the results. Our results also confirms that it's kind of in a linear way. Results. Again, we don't care about these things. Different experimentations. And here we have the conclusion that we can use our adaptive streaming to improve quality. In case we have a fixed energy budget, we can use different compression methods as well. And of course, we can apply our heuristics and our methods to any kind of different wireless technologies. Here we use Wi-Fi, can be applied to any other types of technologies like Bluetooth or maybe 3G or 4G, the upcoming version of 4 technology of the mobile phones. Great. That's all.
Okay, let's thank our speaker. And any questions for the speaker? So we need one question from the audience and you will get a prize. Yes.
Okay, so it's kind of similar, you're just streaming like level of detail basically, but being set by the user.
Yes.
Like texture quality low,
Level of
medium,
detail,
high.
actually, LOD has different meanings.
Yeah, but that's more for the mesh. But
Yes,
texture,
that's more for the mesh.
Yeah.
That's we call it progressive.
Yes.
But it is the first time ever that we are applying the LOD just for the textures,
Okay.
not the 3D meshes.
Yeah.
Because we think that maybe textures are having more sizes than the pure 3D meshes.
Yeah, meshes are usually less.
Yeah.
What do you call a 3D mesh? A 3D texture is very 2D texture, no? It's not a solid texture, right?
Exactly, that's another term. 3D textures here are not kind of imaginary 3D. It's actually 2D applied to a 3D
Yeah,
object.
so those are actually 2D textures. 3D
Yes.
would be solid texture, just usually.
Yes, mostly yes, it is the case. But sometimes we have the coordination here that people say that they are 3D textures in some terms.
Okay.
Can I ask a question?
Yeah, sure.
On what kind of games have you tested your methods?
On which
What
games
do
you
you
test?
mean, what kind of games? Mobile games. I just program my own game.
Is it just specific games? Because sometimes they're different.
This is a demo, a self-runner. No, it's pretty deterministic. You're not playing actually. The player, for instance, is a predefined. The camera, everything is predefined, and something is moving. It's like a demo, self-runner. Not like a real game.
Okay, let's thank our speaker again. Thanks a lot. And 1 moment.